we are working through as many examples as I can from the homework on optimization. So this next question, I'm going to actually show you what it looks like, give you an idea of what you're told, and see where we can go from here. It says the top and bottom margins of a poster are 9 centimeters. So you can see the distance from here to here is 9, and so is there is 9. And on the sides, they are 6 and 6. If the area of the printed material on the poster is fixed at that amount, find the dimensions of the poster with the smallest area. So we are trying to find, essentially, how you can create this to have the printed material. So that green guy there, right, has an area of this, and we've defined the dimensions of the poster. That's the whole thing, with the smallest area. So the big rectangle has to be as small as possible, and that little in-between green one has to be 864. So that is all you're given. So I'm going to start by basically copying that picture. So we have a rectangle that looks like this, roughly. And inside it, there's a smaller rectangle. And I'm going to shade that guy in. And I am going to call this distance X, and I'm going to find this distance Y. Now, once I have figured out what numbers they are, then I'll be adding a 9 and another 9. So it's adding 18. And on this side, I'll add another 6. On this side, I'll add another 6. Because what they want to know is the dimensions of the width, which is this distance. And I think they're calling this the height there. Right. Just basically the same picture with a few extras. The extras are, I'm calling this X, I'm calling this Y. Second thing is that I'm going to make sure that when I'm finished, it's going to be the width that goes here. And it's going to be the height that goes here. And they did tell us that the area of this guy was 864. Well, somehow or other, that needs to be enough information to do everything that we want. So let's start the work here. This distance I'm calling X, this distance I'm calling Y. Since I know that area, the area of the shaded picture is XY. The area is 864 XY. That means Y is 864 over X. And that is important because this is the piece of information that later on I'm going to use to turn everything into X's. Now, we're being asked to optimize the poster. Well, the area of this poster, well, we have to think a little bit hard about this. What is the width? And then multiply that by what is the height. Well, that bit in the middle is called X, okay? Now this piece here is another 6, and this piece here is another 6. So if you drop it down, aren't the combination of those three things the width? Does that make sense? That the width is a 6, an X, and another 6. So that makes it X add 12. Now, if you use the same reasoning, what will be the height?
18y?
18 plus y?
Yeah.
That's what you meant. Okay. And I'll call that P for posters area. And I'll multiply this out, I think. So with FOIL, I'm going to get xy plus 18x plus 12y plus whatever 12 times 18 is, which I'm not going to risk in my head, is 216. This, by the way, is our optimization function, right? This is the one that we're trying to minimize in this particular question, right? Make as small as possible. And you'll notice that there's a y here and there is a y here. And I don't want y's, don't I want this to only have x's? That's where this comes in. So instead of xy, it's x times 864 over x. Then there's an 18x, and then there's a 12. And instead of the y, 864 over x again. And finally, a 216. If you multiply these together, the x's cancel out. You've then got an 18x. This is going to be an ugly fraction. It's going to be a huge ugly fraction. 12 times 864 ugly. So it's 10,368 over x plus another 216. If you add these or combine these together, you get 1,080. Plus 18x plus 10,368 over x. Let me pause at that point. Are you comfortable about how we created the optimization function? We found the width and the height of the poster. Right, the width would be x plus 12. The height, y plus 18. So the area of this big poster, the outside shape, FOIL it all out, and we get an expression that has x's and y's in it. We then use the fact that that shaded area, which is x times y, was 864, and that allowed me to get y in terms of x, which is what we've done. Multiply them out and collect like terms. We good? Okay, so what should I do next? The goal is always to get the optimization function, but what do you do next?
Take the derivative and set it equal to 0.
Nailed it. That's exactly what you do. Normally, so the derivative, I'll call it p dashed. Right, you differentiate a number, you get 0. I know you shouldn't really write 0, but I'm doing it for notes. You differentiate 18x, you get 18. And if you want to differentiate this guy, you should really call it 10,368 x to the -1 and do the power rule, but just to speed things up. Can you trust me that that's what it ends up looking like? So if you differentiate this fraction, that 10,368 over x squared is what you get. Now, just like you went and said, you make it 0. And now the job is to solve an equation involving x. And as long as you do it to both sides, it's okay rule. Any suggestions? There's at least two. Yeah, there are about 2 ways to do this I can think of. Do something to both sides. What do you think might help?
Add 10,036.8 to the other side.
Yes, that's a good start. Now, a little help. Can you see what I might do next?
Times by x squared.
Okay, so you're going to get 18x squared equals 10,368. I've just did cross multiply, but what you said is the same thing. Are you comfortable with that? Where do we go next?
Divide by 18.
Okay. I'm going to check that in the calculator. Hopefully it's a whole number. And it is. Where do we go next then? On a roll here, we're almost finished.
Take the
The
square
square
root.
root.
Exactly. Take a square root, which I'll again hope is a nice number. And would you believe it? It is. So we have just found out the solution value, right? X equals 24 is going to do the job. Now I need to know what Y is equal to. And Y is 864 over X. So it's 864 over 24. Again, I'm going to hope that that's a nice number. So 864 divided by 24. And the answer I got here is 36. So we know the X and we know the Y that solves that puzzle. But if I put 24 in here and I put 36 in here, that would not be the right answer. There's one extra little thing that we need to put in. Now, if the question had just been what is X and what is Y, that would have been the right answer. But the question was, what's the width of this poster, I believe, and what's so what do I do? How do I use these to get the width and the height?
You plug the like the X plus 12 and then the
Okay.
Y plus 18.
Okay, so if this is 24, you add these two together and you'll get 36. And this guy is what, 36, and you add another 18 to it and you get 54. And those are the two numbers that you get in the answer. Can you see that you could do 90% of this question right and then just fall on the last hurdle by not answering what the question wanted to know? The question didn't want to know directly what X and Y is. It wanted to know what the width and height was, right? So if they had said to you, what would be the width and height of the inside rectangle, right? If they said, what's the width and height of the picture? These would have been the numbers. But they said, what's the width and height of the whole poster? Which means it's these two numbers. And that is the end of that question. We're almost, we're going to finish these today. So here is, excuse me, 13. And this is a different situation. Going to set it up for you. 4 feet away from a big tall building, there's a fence. There it is. And we are going to put a ladder so that it just touches the top of the fence, right? Obviously it reaches that. And the fence is 8 feet tall. Now, you could do the fence like that, but couldn't you do the fence like a lot like that? And couldn't you do a fence really close to it? In which case, your ladder would have to be really tall. So it describes the picture, a fence 8 feet tall, got it. Runs parallel to the building, 4 feet away, got it. What is the length in feet of the shortest ladder? This here, I'm going to call X, and X is the length of the ladder. And we are going to somehow or other find the length of this guy. None of the questions we've done today has been even vaguely like this particular one. And it involves us putting in an extra thing that there's no indication in the story that it's necessary, but yet we still need it. So let me show you the extra piece of information that I'm going to use. I'm going to call that angle theta. I'm then going to add a dotted line going here, and I'm going to call that angle also theta. And if you think about it, won't those be the same angle because they're both horizontal lines? Okay. Now, based on what I have just done, this ladder is going to be made up of two pieces, this distance and this distance. So that means X is going to be made up of an A and a B. Now, let's look at this little baby right angle triangle. This angle here is theta. This distance here we don't know. This we know is B, and this distance here we know is 4. I'm going to find B in terms of 4 and the angle theta. Which one of the SOHCAHTOAs uses those guys?
Cosine?
Okay, so the cosine of theta is equal to adjacent over hypotenuse. So far, so good. And if you do a little cross multiplying, B times cosine of theta equals 4. So the cosine of theta is going to be 1. So B is going to be 4 over the cosine of theta. So in this question, X or L, I probably should call it L, but too late now, is going to be made up of a guy called B, which is 4 cosine thetas. Now, if I want to find A, which is this distance, I'll build another right angle triangle. This guy is called A, this angle is called theta, and this distance is 8. Which one of the SOHCAHTOAs works for this triangle?
Sine.
So we have the sine of theta. Essentially what I'm going to do is get A and B in terms of cosine theta. So my equation, my optimization equation is actually going to have thetas in it, not x's. Apart from that, it's going to be pretty much the same. So it's 8 over A. That gets you A sine theta is equal to 8. And that gets you A is 8 over sine theta. I'm beginning to regret picking that X, but it's too late now. So it's going to be this guy, who I'm going to call cosecant theta, and this guy I'm going to call secant theta. So here is the optimization function. And if you like, pretend I said L equals, because X tends to make people think that that's a variable. In this case, the variable is actually theta. So all I need to do is find out when this is 0. Because when this is 0, that's going to be the place where the angle makes the shortest ladder, right? So if you want to differentiate the total distance X with theta, you're going to have to differentiate 8 cosecant thetas and 4 secant thetas. Oh, that is definitely going to test you. Okay, let's do, I think, the easier of the two. What is the derivative of a secant?
Secant times x.
Okay, so it's going to
Times
be
10.
Yeah.
Is it?
secant tangent. You were right. Does anybody know the less common one? Because we don't tend to do this one as much. What is the derivative of 8 secant?
8 cosecant.
Well, there'll be a
times
negative first, right?
cotangent.
Right. So -8. Okay, sorry for interrupting you, but I had to correct it. It's -8, not 8. But after that, what did you say?
Cosecant, cotangent.
Perfect. Now, we have to find what on earth makes that equal to 0. The good news, well, good and bad at the same time, is that normally you would try and do this algebraically, right? You would try and solve, doing things to both sides. Can you trust me that this trig equation just ain't going to do it, right? There isn't any algebraic answer. It's not going to come out as 30 degrees, right? So what it is going to be is plug it into Desmos and find out when it's 0. And if you plug it into Desmos and you want to find out when it's 0, I got the answer here. I haven't got the answer, but I will tell you. It ends up being, oh, shooting space. My calculator was in degrees. So bear with me just a little bit longer. It ends up being 0.9. Whoops. Theta ends up being 0.9. And so what is the smallest, shortest ladder length? 8 cosecants of 0.9 plus 4 secants of 0.9. And that gets us about 16.65 feet. Now I can tell you right now, if I gave that to my Calc 4, I'd be lucky if 10% of them could do it. So if you can follow this one, you're as good as they are. Now that one is unique in many ways, isn't it? Unlike anything we did yesterday. And that's the challenge and the fun of optimization questions. There are so many different kinds, and sometimes you get a really weird one. But it worked, so I'm happy. Yeah, we got time for this one. Here's a really weird one. It's got a big, long instructions. Now I won't bother showing you. I will just draw what you see and explain it. We start off with a person at A, and he's trying to cross this riverbank. And from one side to the other, it's 2 kilometers wide. So it's a pretty big river, right? It's not a stream, 2 kilometers wide. And he wants to reach another point further down here. And for no reason I can think of, instead of him just walking down here and swimming right across, he wants to start here and finish here. Now, he has a point directly across from him called C. And to get to B, he can do a 2-stage journey. He can swim to some point D, and then he can walk from D to B. Now, this point D can move. It can be anywhere you like. In fact, couldn't he just swim straight across to C and then walk down? Couldn't he just swim straight to B and not do any walking, right? So D could be any place between C and B. Would you agree that it would be stupid to swim up here to walk down? And it would be stupid to swim further and walk back. So we're pretty obvious that the right answer is between these two, right? That's just logic. Now, what else do they give us? Well, they tell us things about when he's in the river, what speed he can row at, and when he's on land, what speed he can run at. So let's tell you what those are. When he's on the water, the speed at which he can row is 6 kilometers an hour. And when he is on land, the speed he can run at is 8 kilometers an hour. We are being asked to find the route that would be the quickest. So how could he get from A to B in the quickest way? And you are being asked to tell us I better not call that X, to tell us the distance here. What will they call this? It doesn't matter what letter of the alphabet, it's going to look weird, doesn't it? Z, how about that? I want to keep X for some of the other letters. So we need to find that distance there. And we're going to call that distance Z. So for instance, how far from here to here are they? I think they told me that as well. And the distance from here to here is also 2 kilometers. So if Z ends equaling 0, right? If Z is 0, doesn't that mean go straight across and then run the rest? If Z was equal to 1, it would be, right, go halfway, right, and then walk a kilometer. And if Z was equal to 2, wouldn't that be go straight to there? So we have to figure out the shortest route. And so what we're going to do here, actually, am I going to call that X? I changed my mind. I like X. You know that letter's totally arbitrary. You can call it any letter of the alphabet you like. Decided I like X again. Just the way the question is set up. Now I'm going to add in an invisible dotted line that goes horizontally to make a little right angle triangle. And so T is going to be my optimization function. And T is going to be the total time of whatever journey I take. And that's going to be made up of the time that I spend in the water plus the time I spend running. Would you agree that's the total time, right? How much I spend rowing, right? How much I spend running. Now, let's do the water journey, right? That guy there. That's going to be the distance AD divided by 6, right? You go 6 kilometers and you're traveling whatever AD is. Now, the time you spend running is going to be the distance dB divided by 8, right? Distance over speed is time. Distance over speed is time. Now, I'm going to add in some extra numbers here. If I call this distance x, what will this distance d to b be in terms of x?
2 minus x.
You nailed it.
Or
2 minus x. Don't or it, you're right. So this guy is going to be 2 take away x over 8. Now, this distance AD is going to be the stickler one, right? So I'm just going to separate out the picture, and it looks something like this. C, D, this is x. That dotted distance is 2. There's A. But the distance I want is AD. How will I find the distance AD in terms of x? How will I find AD in terms of x?
Pythagorean theorem?
You will. And so AD squared is 2 squared plus x squared. So AD is the square root of that. And you cannot do anything to that. That is not 2 plus x. It is that ugly square root. So we now have the distance AD in terms of x. Did you notice that this question didn't have a y guy, you know, an x and a y, right? Now, maybe it's not the prettiest equation in the world, because it certainly isn't, but that is the optimization function, right? The guy that we're trying to maximize or minimize. In this case, don't we want to make this as small as possible, right? So we're looking for a 0 that generates that. Well, this is going to cause some problems. Let's differentiate it. This guy here is not really ready to be differentiated yet. You agree? What is the problem with differentiating that? How should it be written so that I can differentiate it? What should we write the square root as?
To the power of 1/2.
Okay. Now, thinking of it like that, it's 1/2 4 plus x squared, reduce the power by 1, and then notice it's a chain rule. So the derivative of the inside function is 2x. And just put that whole thing over 6. Now, if you want to differentiate this guy, you get -1 and put the whole thing over 8. And now I'm going to make this as pretty as I can. That times that cancels and you get an x. This guy comes downstairs and you're going to get a 4 plus x squared minus an 8. But we're trying to solve when is that guy equal to 0. Are we good so far? Now, solving equations is never easy because there's so many different kinds of equations, but we do have one method that kind of gets us out of trouble almost all the time. And isn't that as long as you do it to both sides, it's okay rule. So I'm going to solve that equation and we are going to get a really weird answer, and that's okay. So I'm going to add 1/8 to both sides. Okay, what should I do next?
Times by 6, maybe?
Say that again?
Maybe times by 6?
You could, and that would help a little bit, but could we maybe do a little bit more? Here's a little clue.
cross multiply.
Yeah. So 8 times x is equal to 6, 4 plus x squared. If you ever see two fractions right equal to each other, cross multiply is normally a good way of getting rid of the fractions. Even if it's only one fraction equals something, the something, if you put it over 1, allows you to do the cross multiply as well. Now, you said divide by 6. I kind of like that idea of dividing by 6, so I'm going to do it now. And probably I should have simplified it while I was at it. Now, no matter how weird an equation is, as long as you do it to both sides, we'll get you out of a whole load of trouble. Now you look at this, it's 4/3 x essentially, right? Can live with that, but ooh, don't like the looks of this, right? Square root of 4 plus x squared. Wouldn't you like that square root to go away? I mean, isn't that the guy that's causing the trouble right now? So how would you make a square root go away? What would you do to both sides?
Square root.
Okay. And if you square this guy just to save a line of working, can you trust me you get that? Square this guy, square these guys. We're getting really close to the final answer. What will you do to both sides next?
Multiply by 9.
Okay. That's not the way my brain's working, but that works fine. I like it. Nothing wrong with that. It's just not the way I thought about it. Okay, what do we do now?
Move over the 9 to the other side, and then factor out of x squared.
Right, so we got to there. So what do we do next?
Divide by 7.
I know it took a long time, but we did get there, didn't we? What do we do now?
Take the square root.
Take a square root. And I said something weird is going to happen. Doesn't look like anything weird has happened yet. Oh, the answer is x equals 6 over the square root of 7. And you'd say, hey, that's it. Well, let's show you the weird part now. 6 divided by the square root of 7 is actually 2.3 roughly. We've not found actually the best answer at all. We've actually found the worst answer. Right? So you then have to say, well, what on earth is the quickest way to get from here to here? And the answer is just go straight. Now, this is the only question that we've came across where the answer that we got to our answer, or to our puzzle, whatever you want to call it, wasn't the best answer. It was actually the worst answer. If you use 2.3, wouldn't you sail right by the place and then walk back to it? Would you agree that wouldn't be the quickest? So why don't you just sail straight to it and cut out the middleman with the walk back? Now, why did calculus come up with this? Don't know. Except calculus doesn't know that it has a goal. It just does what it does. And it generates the best answer, but it also can generate the worst answer, can't it? And that would have been one of the worst answers to do what that number said. I thought that was weird for a different reason. And we have one last question. And this is 15. 15 is not weird. 15 is just ugly. So you've got a place here called A and another place here called P. And then you've got a place over here called B, little invisible dotted line going that way and another one going this way. And another one away over here called C. So a point P, that's this one, needs to be located somewhere on the line AD, right? So you could put it here, you could put it down here, you could put it away up here. But it needs to be done in such a way to minimize the total length of these three. So this in mathematics is called a graphing problem, not graphing as in like fx equals x cubed. Graphing is a name that we give when you are trying to connect points together and you want to do them in such a way. So can you imagine that you had three different towns and you were trying to connect them with the shortest road that would allow you to get to all three? Now you could say, well, I would just do a road there and a road there, but that would be maybe too much money, right? So what you might choose to do is pick a place like outside of the three towns and make a little T junction thing, right? So maybe you're trying to create power grids to a city. Maybe it's a sewerage system, whatever it is, these three guys have to be minimized. So T is going to be the total distance. And the total distance, I'm going to call it T when I'm finished. And we are told that this distance from here to here is 4 miles, and that this is 1 mile, and that this side is 3 miles. And so I am going to create our optimization question. And the total distance is AP, that distance, which I'm going to call X because I want to. Then it's going to be P to B plus P to C. Would you agree that's the total distance of the three roads added up? Now, you notice I picked that one to call X because I wanted one of them to be nice. I now need to find this distance PB. From the top to the bottom, it's 4. This piece is X. How much is this dotted line PD? What's that going to be in terms of X? This is 4. This piece is X. What's this piece?
4 minus X.
Now, if I build a little right angle triangle, this guy is 4 minus X. This distance is 1. Can you see I can now find BP? And BP, and I'm running short of time, so I'm cutting out a whole load of guys, is Pythagoras. It's 1 squared plus that guy squared. Can you trust me on that? So it's the square root of 1 squared 4 minus X squared. Now, if you want to do PC, similar kind of situation, only this distance here is 3, this is still 4 minus X, and this is PC. And if you use Pythagoras, it's going to be 3 squared plus 4 minus X squared. So it's going to be the square root of 3 squared plus 4 minus X squared. That's pretty much all I have time for. Now, what if we had longer time, what I would have done next is, wouldn't I FOIL that all out and make it look pretty? Wouldn't I FOIL that all out and make it look pretty? And that would be my optimization function. I would then differentiate it. And I'd get 1 plus an ugly guy plus another ugly guy. Can you imagine what these would look like, right? Pretty messy derivatives. And then you would try and solve when is it equal to 0. But you wouldn't be able to do it algebraically because it's just too ugly to solve. So what you'll do instead is plug it into Desmos. And when you plug it into Desmos, it tells you, at least in this case, that you make X 3.04, and that when you calculate the total distance, it ends up being 7.58. I guess I should say miles. Okay, last name and bye-bye. That is us for today. And we did, you know, though I kind of had to push the last one, we did get them all done. That's them finished. Hopefully you can fill in the gaps when you do your homework.
Thank you.
Okay, bye-bye for now. As I say, I'll